Hi. Today is the third in our series of videos on the disease, or the human malware, as I've been advised to say. The first video just went through some overviews of some food recommendations and the use of hand wipe and cleaning materials, as well as wearing masks. In the second video, we really went into more detail about washing your hands, use of gloves, masks, and how to formulate your own disinfectant solutions. Based on the comments and the controversies that were developed in those first two videos, I decided to produce this third video to address some of the questions as well as the controversies that came up in the comment section. The single biggest controversy was my recommendations regarding the inconsistent statements by the World Health Organization on the use of masks. Their statements were that these masks are only necessary to be worn by people with the virus, to keep the virus from contaminating other people. And they said, therefore, you shouldn't be wearing the masks. But at the same time, they were saying you should not be wearing these masks because they need to be made available to healthcare providers. That's inconsistent. It can't be both. It has to be either or. If the masks don't work, the healthcare providers don't need them. And if they do work, then they will benefit you. And the real question is the justification for allowing people to believe that they shouldn't be using the masks because they don't work. That's where I have a disagreement with the way that they've tried to accomplish their ends. And so I will leave you with a new way to view this argument, and that is, do you really believe, if we had enough masks, that the same agencies that tell us that we should wear seatbelts and bike helmets and use trigger locks and get plenty of exercise and eat healthy would tell us not to wear these masks? I don't think so. Now, the other questions that came out were, are there different types of methodologies available to decontaminate rooms and surfaces? The most interesting one, the most common one, was the use of UV or germicidal light. UV light is very good as a disinfectant because it not only kills the viruses on the surfaces, bacteria as well, that it strikes, but it also kills bacteria and viruses that can be airborne between the generator and the surfaces that they strike. And because UV light can be produced by a single generator, placed inside of an operating room or an ICU or a procedure room, even in the passenger compartment of an airplane, it saves a lot of man hours and eliminates the need for technicians to move around in those environments and have to contact all the surfaces, so it protects them. The way UV light works is that there are bands of UV. The longest wavelength UV, called UVA, is just below the visible range. That's the party black light range. UVB is a shorter wavelength that causes sunburns and tanning. UVC, centered around about 250 nanometers, is the germicidal wavelength. At that short enough wavelength, the light is actually able to destroy or tear apart the RNA molecules inside the virus and prevent it from being able to reproduce. And UV light, typically in these big machines that are put in operating rooms, is generated by a pulsed xenon light source. This is a pulsed xenon light that we use in our big laser over there in the other end of the room. But these things can produce kilowatts of UV output and are very effective at sterilizing surfaces. The one issue with any of these types of UV lights, though, is that there is an issue with shading or shadowing. So often a technician will go into an operating room with one of these powerful units, set it up, run it for 10 or 15 minutes, then shut it down and move it to a new location so that none of the tables and the objects within the room will provide protection from any of the surfaces. The fields will overlap so that you get a full illumination of the room. Now, to kill the viruses, you don't need very much energy. Depending on what papers you read, it requires anywhere from about 50 to about 200 joules per meter, or watts for a second per meter. And if you think about a room that is 10 feet by 10 feet by 10 feet, or 3 by 3 by 3 meters, it has a surface area of 60 square meters. And if you put a bunch of stuff in there, say 120 square meters of surface area, even at the high end of the range of the lethality for viruses of 200 watts per meter, or watt seconds, you need 24,000 watts for 1 second to sterilize the inside of a room like that. Now that may sound like a lot of power, and you might think you need these really powerful lamps to do that, but you don't. There are commercial sources, like I'm showing you right here, that manufacture germicidal lamps based on low pressure mercury discharge. Mercury is remarkable in that it's one of the most efficient light sources out there. It generates the bulk of its energy right in the middle of the UVC band at 254 nanometers. About 1/3 of all the power that's put into a UV germicidal lamp comes out in usable light. And because the technology is the same that's used to build fluorescent lamps, effectively a low pressure mercury discharge inside the fluorescent lamp illuminates the inside where the phosphors are, causes the phosphor to glow, and that's what's illuminating the room right now that we're talking in. If the bulb jacket is manufactured from a material that can transmit 254 nanometers and you leave out the phosphor, you have a germicidal lamp. So the same form factors for the lamps can be used to support a germicidal lamp and a fluorescent lamp. They come in the compact fluorescent variety, they come in the linear T5, T8, T12 variety, and they can be powered by typical fluorescent ballasts. Interesting little aside, did you know that the numbers associated with those linear tubes, T5, T8, T12, represents the number of eighths of an inch of diameter of the jacket. So the lights in this room are T5 lamps, they're 5/8 of an inch in diameter. Anyway, a typical T8 lamp will use about 30 watts, and that means it will produce about 10 watts of usable UV light. In 1 hour, 3,600 seconds, you will illuminate that 3 by 3 by 3 meter room that I talked about at 36,000 watt seconds, or 1.5 times the high level necessary to sterilize the room. So it's very effective. Now, you may not be in an environment where you have to constantly decontaminate your rooms. You may want to decontaminate materials like clothes, shoes, masks. One of the issues with any kind of porous or soft surface is that the UV light is so strongly absorbed in the surface layers, it may not penetrate very effectively into the material. Now, effectively, if you've got a powerful light like this, you could just fry the thing in order to get enough light that will actually penetrate inside. Problem is, UVC light also damages the polypropylene fibers in a mask, and so that's why plastics will chalk in the sunlight. So if you were to get enough illumination to kill the viruses, you also may decrease the functionality of the mask. So it may not be the way that you want to try to sterilize a porous surface. For that purpose, you might want to look at ozone. Ozone is an interesting material because it's basically an O3 molecule, and it is formed by some energetic process, either through UV light, these lamps will make a little of it, or through a discharge. And it will create free oxygen atoms out of an O2 molecule. And those are very unstable, very reactive, and they will often stick right back together again. But if they happen to be near another oxygen molecule, they can form a slightly more stable O3 bond, an O3 molecule, which when it contacts surfaces or freon in the atmosphere or a viral capsule, will decompose back to oxygen, and this very, very reactive oxygen atom, which denatures, fries, burns, oxidizes the capsule and destroys the virus. It is so powerful that even at parts below 1 part per million, even at concentrations below 1 part per million, it's pretty lethal. And we'll put a link to an article in the description below this video where they give a lot of information about how it's been used to kill not only bacteria, but viruses similar to the viruses that are bothering us right now. To get an idea of how much ozone that really is, 1 part per million in this very large room is 0.5 gram of ozone, or 500 cc's. And the most efficient way to generate it is what's called a dielectric barrier discharge. Sounds fancy, really simple. If you take a glass tube, like I have right here down on the table, and you place inside of that tube a conductor, like an aluminum or a stainless steel rod or a tube, that fits inside of the glass tube. Then simply wrap the tube in some conductor like aluminum foil, keeping the spacings on all the ends and edges and conductors far enough apart, and hook them up to a high voltage supply that will develop about 1,000 or 2,000 volts. The glass will hold up to tens of thousands of volts. You won't get a spark, you won't get an arc. But the very high fields that are created between those close conductors are enough to effectively tear apart the oxygen or the nitrogen and allow them to form this new ozone molecule. I've got this thing hooked up right here to an oxygen tank. You could hook it up to a simple aquarium pump. The only disadvantage of using air versus oxygen is you'll also produce some nitric oxides in the process. It's probably also going to kill the viruses, so I wouldn't worry about that. This is about 0.5% efficient, so you'll make about 5,000 parts per million using an air pump like this, and you'll make about 50,000 parts per million when you're using pure oxygen. When I turn this on, what you're going to hear is sort of a hissing and a popping sound. Now, if you listen through my microphone, let's see if you can hear that right now. There are no arcs, there are no sparks, but what you're hearing, just like in an ultrasonic cleaner, is that we're forming very briefly little separate atoms that are connecting back again, and as they slam back together, they cause these little pops and these little detonations, and that's why we're hearing this hissing and this fizzing sound. But when I do that, I'm also creating a lot of ozone. If I flow just a small quantity of oxygen through here, and then I turn on the high voltage, within a second, you can smell the very strong smell of ozone within the room. And if you put your nose even this far away, you'll start to feel some burning, almost like there's hot sauce in your nose. Essence of thunderstorm. It's kind of a fresh smell. This is a very effective disinfectant, and as I said, it's very easy to make. And for a little test, what I did is I threw some yeast and some sugar into these 2 beakers and made this as a single compound, divided it up so it's exactly the same amount of sugar and yeast. In this, I just let it grow for about an hour. In this, I bubbled for about 4 or 5 seconds some of the ozone into the water here. And as you can see, no growth. In here, you can see this is already starting to foam up. It kills spores, it kills viruses, it kills bacteria. And a convenient way that you can use this with porous substances is you can take a tube, like I've built here, and simply feed it into one of these clothes vacuum bags. These are the type of bags that you'll put blankets and old clothes in. Suck them down with a shop vac in order to pack them in your attic. But as we did with our helium experiments, this is an excellent way to be able to fill a contained space with the ozone and let it soak any of the porous materials that you might want to treat. You can treat old shoes, socks, clothes, even the masks. Now, one of the downsides, though, of using something like this in order to treat something as mission critical as the masks is that I know we've got plenty of ozone to be able to kill the spores and the bacteria, but we don't want to use so much that we again deteriorate the plastic, the polypropylene plastic. And I can't guarantee a certain number of parts per million if I try to hold back. So there's a little bit of an uncertainty in terms of how clean I've really made it. You might also think, well, I don't have a high voltage transformer and I don't want to work with high voltages. Obviously, this has got some risk. You'd have to put this in a safe container away from kids, away from somebody who might accidentally touch this. I think probably the least sort of theoretical way to clean off these masks so that you could use them again and again and again would simply be to use alcohol. Because these are made out of polypropylene fibers and they are ultrasonically welded, there's no adhesives in here, it's just polypropylene. And polypropylene is immune to the alcohols. You can even store alcohol in polypropylene bottles. So what I did is I took some of these masks and just getting a canning jar, this is a 2-liter canning jar, and I demonstrated that the masks themselves will wet. They will soak all the way through. By pouring the alcohol through in here, you can see that it drips through, it penetrates, and it wets the surface. So there's no question that this is getting all the way through the mask. What I then did is I took these masks, like this, and simply placed them in the jar, dumped in a quantity of alcohol, put the top on, shook them up, and I've tested 3 masks now with as many as 4 cycles and up to 24 hours of soaking in this alcohol. Once you've had about 5 minutes of soaking, based on the article that again we will post or we will link in the description below the video, 5 minutes is sort of the longest amount of time you would need to get over the 99% kill rate on this virus. You then take the mask out, and once you remove the mask from the jar, the only alcohol that you're going to be removing from the jar is what is soaking the mask. So theoretically, you could reuse this alcohol again and again and again. And if you just take this mask and allow it to air dry, within about an hour, it feels dry. And within about an hour and a half, you can't even smell the alcohol. And just to let you know, both of these masks here have been processed 4 times. There's no apparent effect from the alcohol. You can't even tell that I did this. So it's a very effective way of cleaning the masks. It's very reliable. It uses very little alcohol. And the only problem you might say is, well, I can't even buy any alcohol anymore. Well, don't use this. This is denatured alcohol from the hardware store. And although hardware store solvents are notorious for being relatively unpure, this is just a whole new level of unpure. This has been intentionally poisoned to make it undrinkable. And they will put all kinds of materials in here. It could be methanol, it can be acetone, gasoline, stinky sulfur compounds. They won't even tell you how much. They won't tell you what. And it changes or it varies between manufacturers. So it's a completely unreliable solvent. I don't even use this with epoxy work. I just use this to start fires outside. The pharmacy type of isopropyl alcohol is excellent. And this leaves no residue. There is nothing else in here other than isopropyl and water. Now, one of the difficulties you might have is that the percentages that are available are becoming more and more limited. The optimal percentage to use is 70%. As I said in the last video, higher percentages tend not to penetrate the virus very deeply before they try to kill it, and lower percentages are just not potent enough. 70% is the target concentration. Now, if it turns out that all you can get is, say, 50% isopropyl, if you take advantage of some laboratory equipment like we have, or a still, as you might see in some of our other videos, we get into distillation. The difficulty in concentrating this all the way up to 90% or 70% is minimal. This is one of the easiest distillations you can do. But if it turns out that you don't have access to distillation equipment, if it turns out that where you live in the world you can't do the moonshine, you can't use bananas and brandy and barleys and sugars to make your own alcohol and distill it, another thing is you can actually go to the liquor store and you can get Everclear. This comes up to like 191 proof, but the 151 is right in the middle of the target range at 75% alcohol. This is excellent. Even this is being bought up. So another trick you might use is get the most concentrated vodka, cheapest rot gut that you can buy on the lowest part of the shelves, at 100 proof or effectively 50% alcohol, and mixing it with the 90%, 1-to-1, you'll end up with a 70% concentration and you'll double the amount of the isopropyl that you've got on hand. So it's, again, another way to extend this. So it doesn't really matter how you decide to approach this. You can either use high-tech, you can use low-tech, but it's all just tech ingredients. Now, I read all of the comments, and I really appreciate if you leave them because I try to answer as many of the questions that you have. And if you like the kind of information that we're providing here, please subscribe to the channel because we've got more videos coming, and not all of them are based on such a grim topic as what we're dealing with today. Most of them are informational, they're exciting, they're interesting, and we've got a large library of them already available, and we're doing some pretty interesting things right now. We're working on the ultrasonic sterilizers and cleaners, the speakers, the generators, the flexible armor. There's a whole bunch of things that are coming up. And so we're going to move on beyond the videos that we've been covering recently. But also, if you find that this is useful, please share this with anybody you know, because I think you're going to find that this kind of information is not always available to everybody out there. Not all the people that are watching these videos need this information, and sometimes the people that don't see them are the ones that need it the most. So I want to thank you very much for watching. Please subscribe, and don't